Mr. Chairman, for introduction. In fact, this title and this project was related to former European project, and now we have continuation supported by Polish project. And we had long discussion also with Professor Giuseppe Rega on different problems related to this dynamics of thin wall rotating composite beam. And the plan of our presentation is like this. I will show motivation for this, and then some basic formulas and derivation of partial differential equation, reduction to ordinary differential equations, and some exemplary results related to mode couplings, and also some next steps which we are going to do. And I will start from motivation, and we have some models on helicopter blades, but not necessarily helicopter, rotating structure. You can see the small scale model, which is like this. This is not nano model. This is 30 centimeters small model. This is this scale. And another one, this is middle scale model, which is a copy, a model of real helicopter blade. This is just a beam, and this is the copy of helicopter blade in scale 1 to 6, and we are going in the next step to go to this direction. This is, you see the experimental part with some pointers. We want to measure vibration by using two high-speed cameras, and in this way we will detect this. And also another problem which is included with this is active control of the vibration. You can see embedded active elements, actuators, PZT actuators, and these actuators are actuated by this amplifier and by the sliding rings. We can put voltage, and we can activate and control behavior of this structure. And this is a short movie to show you. I don't know which one, the first one?
Yes, maybe.
This is just to show you that it really works, and you are interested in dynamics of such a structure. And we can control also the angular speed. It is not necessary to have constant angular speed. We can have different dynamics behavior. And the model is presented here. We consider the hub, which is a solid body, and to this solid body there is the flexible beam, which is fixed, and this beam is made of composite. This is important because we want to model composite structure, and this this structure, the beam can have some preset angle. You see here, and this preset angle we can change. And also angular velocity, as I said, is not necessarily constant, can vary. And the cross-section of the beam you see here can be open or closed, but this is thin wall structure made of composite with different structural configuration of plies which are applied to this beam. And what is important, we can distinguish two important coordinates. The first, this is midline, which is the index is 0. It means that all displacement with 0 are related to midline of the cross section. And arbitrary point A, there are displacement denoted by d, x, y, z, respectively. And this is the notation. And of course, we want to have very general model, but of course it is not so easy to derive very general model, and we did some assumption. The first assumption is that the cross section of the beam behaves as a solid body. It means that the original box shape is preserved, and there is no change in this direction. But we consider primary and secondary warping. It means we allow to have deformation in elongation along an x direction. And of course, we take into account shear deformation, which is related in two directions, which is related to Timoshenko theory. And also, we neglected some transverse normal direction stresses and hoop stresses because we consider thin wall structure, which is neglected. And also assume that initial configuration, the beam is a straight line and there is no pre-twist and no pre-con angles. But we can modify this, and also it can be included if we want to do this in next step. And this is configuration again. We also introduce local coordinate, which is curvilinear coordinate system in tangential, normal, and longitudinal directions. And we studied two types of cross-section, which is rectangular, which is closed cross-section. We can change this shape easily. It can be given any function, and we can compute the dynamics for any profile. And this is the classical beam, and this profile belongs to so-called open cross-section. Okay. And we started from the beginning, from the Hamilton principle. And apart from kinetic and potential energy, we also included external non-conservative forces, which can be useful to study influence of aerodynamic forces, for example, or other forces, external forces, and we can include in this model. And then we formulated potential energy, and we assume linear material properties, and also in kinetic energy, you see there is the radius vector in absolute coordinate, should be transformed from local coordinate. I'm not going to detail, but there is preset angle, which is theta, and angular rotation angle, which is psi, not necessarily constant. And then we can find deflections for arbitrary point in 3 directions. And what is important in this, that we have to include some nonlinear terms. They are important. In rotating structure, there are some cosinus and sinus function. If we approximate, for example, this cosinus, keeping perturbations orders, and we take only the first term as a 1, then we neglect very important terms. We have to take, sorry about this, we have to take, this should be below, we have to take quadratic term here to keep influence of the centrifugal force. It is essential. Okay. And then we go to nonlinear stress strain, and this is the nonlinear part. We have to keep this. This is important. And we have also a warping function of the first kind. It means that it's warping of the midline of the profile, which is warping of the general profile, and a warping function of the second kind, which is here, G1, which is warping due to thickness of the wall. This is another warping. And finally, we taking into account layers, number of layers. This is n layers n plies of the composites, and integrating through the thickness of each layer, we get to membrane forces. We get membrane forces, transverse forces, and stress couples. Of course, because the wall is very thin, we assume that this LSS, this moment is equal to 0. Okay. And then we have defined axial force, shear force in 2 directions, twisting moment, bending moment in 2 directions, warping torque, so-called B moment, and also moment related to centrifugal force. And now we decided to try a specific configuration. First, we studied so-called CUS configuration, which is circumferentially uniform stiffness, which is symmetric, and this one. And then we moved to this one, which is circumferentially asymmetric stiffness, which is the specific case of the composite fibers orientation, which is similar to the stripe which we put on, for example, on tennis rocket handle. If we put something like this, this is the localization of the reinforcing fibers. Why this is important? Because in this configuration, this is very specific. We have the highest possible coupling with bending, flapwise bending, and twist. If we put one actuator in the next step, we can bend and immediately twist the structure. And this is the best configuration. We tested this. And also, there are two sets of equations. Three of them are coupled, twist and bending, and another three, this is axial and Hortwise shear and bending on opposite direction, and axial displacement are also coupled. And then we decided to the CAA configuration, asymmetric stiffness. Then some terms are different than 0. These terms are different than 0, and these terms are different than 0. Rest are equal to 0. And this is simple, specific case. And finally, we get to this reduced model. We take into account only three equations. It means bending, twisting, and rotation of the cross-section due to Timoshenko effect. And we have, and this is driving equation, which is related to hub motion. And everything is coupled, and there are boundary conditions. And now we have to reduce the problem from ordinary differential equation to from partial to ordinary differential equations. Before this, we have also the axial force here is included, and we have to find this axial force. And this axial force we found from the another set of equations from longitudinal direction, and it was possible to find after some reduction. We neglected inertia term, and we neglected this term as a small, and then it was possible to integrate, and we got this. And also we decided to add one nonlinear term, as you can see here, because we think that maybe it can be essential. We are not sure about this. We put some Heaviside function. We can have it as a 0 or 1, and we can see the influence of this part. We added this, and finally we use this to the final equations. And there are practical delta. Small scale for me is 25 centimeters. This is the example. The beam, the thickness is 1 millimeter. 1 millimeter. And there are data. This is graphic epoxy laminate. And we computed this CAA configuration. And the most important is A37 parameter, because this parameter couples twist and bending. And we see that the maximal coupling is for this peak here. And this is about 75 degrees for the reinforcing fibers orientation. And having this maximum, we computed a rest of coefficient. And now we are working on this maximum coupling. And for this set, we reduce the problem. And of course, we use Galerkin method, but we take into account admissible function, which satisfies only geometric boundary conditions. And for bending, we use Chebyshev polynomials of the first kind. For rotation of a cross-section, sinus functions. And for twisting, we use monomials. And finally, we were able to find modes, and we selected 3 vibration modes, which has to satisfy boundary condition like this. And the mode is complex. The mode includes bending, twisting, and rotation of cross-section. This is complex mode. And there are modes. This is the first mode for different angular speed, 400 and 900. But we see that for this configuration, 75 degrees, the difference between modes is small. It means that for reduction, we can apply cantilever beam, just cantilever beam mode. But if we change the angle, for example, you see for 15 degrees, different coupling, the difference between modes for different angular speed is essential. And maybe, this is our conclusion, for composite structure, in certain situation, to do reduction, we have to take into account average angular speed to have reduction around this angular speed. This is our conclusion. And finally, we got this equation, single mode reduction, which is complex mode, twist and bending. And we got equation for the beam, equation for the hub, driving equation, which are coupled by the second derivative, you can see. And it is, if we reject all nonlinear terms, we get 2 linear equations, and putting omega as a constant for one moment, just to see what happened, we got natural frequency of the full system, hub beam system. And we see that we can consider the beam as a cantilever, rotating cantilever in coma, only if the hub inertia tends to infinity. If we take into account that, for example, hub inertia is equal to inertia of the beam, this is the function, the figure shows influence of the natural frequency of hub beam system versus mass moment of inertia of the hub, which is relative to the beam inertia. If there is 1 to 1, for example, there is difference in natural frequency of the system, and this is important. If we go to infinity with this, then we go to cantilever beam system. Of course, if we change angular speed, we get another curve. And and we tested, okay, I'm finishing, and we tested the structure just now without any fluid interaction, just we took into account the torque, which can be given by different functions, and we tested for sinus function to check or constant torque plus sinus. And we got such a curve. This is the resonance for the beam we got, and this is a resonance for the hub. But in this point, in the hub motion, this is angular velocity of the hub. In this point, which is natural frequency of the cantilever beam, we get anti-resonance, something like anti-resonance due to interaction between hub and the beam. And we have to remember about this, which is important. And the hub influence, we see that resonance vary from very light hub, and we change the mass moment of inertia to heavy hub. We are here as big difference in natural frequency, and this is hub response, angular velocity. We see the also change from very light hub to heavy hub. Okay, and also we tested Coriolis influence. If we put the solution with Coriolis force and without Coriolis force, we don't observe difference on this diagram, on this oscillation diagram, but I subtracted one from another, and we see some difference, but this difference is not important. But for certain configuration of fibers, we think it can be essential. And we are studying on this Coriolis influence for specific composite configuration. This is important or not in some cases for this. And I'm finishing, and of course, another important part is if we assume translation of the hub additionally, which is in practice observable. If we have small oscillation in one and second direction, immediately in the model we get strongly nonlinear term, which is, this is acceleration of the hub in one direction, and it is coupled with coordinate and nonlinear cosinus function, which is nonlinear parametric excitation immediately. If we assume oscillation of the hub or constant acceleration, we get strongly nonlinear parametric term and also external excitation terms. They are included. we are working on this. And also control, we tried saturation control for rotating structure, and we got some preliminary results, but we are thinking, we are trying to find influence of the angular speed on this nonlinear control. And it seems if angular speed increases, this area is narrow, very narrow, and it can be difficult maybe to use this. And just to conclude, the first observation is in composite structure we have to take into account angular speed for formulation of the normal modes. For specific configuration can be important. The second, and we can find maximum coupling between bending and twisting, and we can use this to control the structure. Band 1 actuator can twist two types of deformation. And also we have to remember the hub inertia is essential. We have to take into account and study full system dynamics, and also Coriolis non-constant rotation, also possible translation of the hub can give important nonlinear terms. Okay, thank you very much.
Thank you very much, Jerzy. We have time just for one quick question because we are late, please.
But I'm interested in control. Could you please comment what kind of control you apply, specifically what you control, what's your control algorithm, etc.?
Okay, we can use very classical PID control, and you can do this, but we try to more artificial, and we use nonlinear controller developed by Professor Knife, the saturation control, which is additional oscillator nonlinear coupled with the basic structure by quadratic term. And we can use some profits from this coupling. But for rotating structure, we have to think, is it advantage or not? We have to think.
Okay.
There are many different techniques.
Marian, very quick, very quick.
Your analysis is for hub and one beam.
Okay, in this moment, yes.
My question is, you probably want to apply that for the helicopter, where
Yes.
the structures are built to be symmetric, some of the effect to be nullified and so on. And what is the quick answer? And the second thing is, why did you start with the beam, which is basically thin wall? How the thin wall structure is actually influencing, apart from making things more complicated, the dynamics of the system?
Okay, the first question is quick. Now we are working on two-blade rotor, and it is very easy to generalize to n numbers of blades. I can do this. Of course, this problem is more complex.